So again we come to the definitions of the ideal, principal ideal. See, in the principal ideal, the principal ideal. So what is the principal ideal? Main aim is, suppose if we take in Z, see Z. So Z is contains set of all, Z is contains set of all minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, etc. etc. This is that. Suppose I multiply this Z as an element 2, as element. Suppose if I take a subset of this, subset is either 5Z. What is a 5Z? Is minus 10, minus 5, 0, 5, 10, etc. Minus 5 is 5, 10. Here, 5 play an important role. I am multiplying that 5. Multiplying 5 is an element in Z. So multiply. We get minus 10, minus 5, 0, 5, 10, etc. See, phi of Z is same as is subset of Z. So a phi is the generator of this set. Phi is the generator of this set. So I write an ideal S of a ring R is said to be a principal ideal. Is said to be a principal ideal if there exists an element A belongs to S. If there exists element A belongs to S, such that and the ideal, an ideal T of R, an ideal T of R containing A, T of R containing A, also containing S, that is, you say S of S equal to A. So A is in form of a generator. We multiply that element, we get that. For example, if we take, suppose we are to find the principal ideal generated by phi in the ring of integer. The ring Z of integer is a commutative ring with unity. So not only phi, suppose if we take a Z, I am multiplying 3. So multiplying 3, what do you get? Minus 9, minus 6, minus 3, 0, 3, 6, 9, etc. etc. See here, this is also Z. This is also subset of Z. 3Z is also subset of Z. 3Z is also subset of Z. But here 3 is generated. You are multiplying 3 times of this whole element we get it. So here 3Z. So phi of this is a generator phi equal to set of all phi R belongs to Z. R belongs to Z. So we take phi is generator, so it will be set of all minus 10, minus 5, 0, 5, 10. Obviously, minus 5 of this will be 5. The definitions, if A not equal to 0, A is an element of a ring, so A is an element of a commutative ring R, then A is said to be divides A said to be divides B belongs to R. There exists an element C belongs to R, such that B equal to C. So this is, we come to the next associative property, that so a ring in which every ideal is a principal ideal. Every ideal is a principal ideal, but principal ideal may not be an ideals. A ring in which every ideal is a principal ideal is called a principal ideal ring. Thus, an ideal generated by a single element itself is called a principal ideal. Ideal generated by a single element itself is called principal ideal. Now, if in a ring or as a unit element 1 and as a unit element 1, then the ideal generated by 1 is the whole ring. So we know just if Z is something, if we multiply 1 into Z is same set, that is 1. 1 is a whole ring. 1 is a generator, is a whole ring, as simply said. If a ring or as a unit element 1, then the ideal generated by 1 is the whole ring. 1 R of this equal to R, since every element R belongs to R, may be written as R into 1. For this reason, ring itself is called unit ideal. Ring itself is called unit ideal. The ideal generated by the 0 element R, that is 0 consists of 0 element alone, and it is called a null ideal. See, in a set Z, So if we multiply 1 into z, itself is a z. Itself is a z. So if we multiply 0 into that times, we get a null ideals. Null. If we do 0 times of that, all element will get 0. That is called null ideals. Null ideal. So in this case, every ring R has at least one principal ideals, namely a 0. Every ring with unity has at least two principal ideal, namely 0 and 1. So the principal ideal you get here, if you multiply that 0 element, all the element is 0. If you multiply 1 times of z, we get a whole z. That is there. Yeah, at least two principal ideal, namely 0 and 1. Now, by using the definition of principal ideal, I prove the simple theorem on the principal ideal. If A is an element in a commutative ring or with unity, A is an element in a commutative ring or with the unity, then the set S equal to set of all RA, S equal to set of all RA for X such that R belongs to R is a principal ideal. R belongs to R is a principal ideal of R generated by element A. Generated by element A, that is S equal to of A. A generator of A. That is, we extend that using the theorem, we extend that. So we get a multiplier of that elements, we get whole the set, whole the integer, whole integer. Multiplying that times, we get that. So this is called the element is a commutator. This is a principal ideal theorem. Principal ideal theorem. Using that, here we next session approve a theorem on principal ideal ring. So theorem on a principal ideal ring. So basically we need a generator here. So 1 into A into 1 I get.